Hello, everyone. I'm Reshma Sheikh. I'm on the programming committee for MLconf. I'd like to introduce our two speakers next. There is Isaac Joseph and Cristine Marsh, and their title is Applied Machine Learning. They're Applied Machine Learning Scientists at a firm, Shparkley, Scaling Shapley Values with Spark.
Great, thanks. So as just mentioned, I'm Isaac. I'm a software engineer on the machine learning team, and here are some ways to get in contact with me.
And I am Cristine. I am a applied machine learning scientist on the fraud team specifically. And I'm going to also introduce Affirm as a company. So next slide. So if you have not heard of Affirm, then we offer point of sale loans for our customers. Can you go next slide? Yay. Sorry, can we go to the Affirm slide?
Sorry.
So Affirm offers point of sale loans for our customers. Our applied machine learning team creates models for credit risk decisioning, fraud detection, and personalizing a customer's experience. Our machine learning engineering team productionizes models and creates platform for model training. So now let's go and do an overview about what we're going to talk about today. Next slide. So being able to make sure that models are fair and interpretable is very important for all machine learning applications, but it's also particularly important in lending. For credit, we need to be able to explain why they were rejected for fair lending reasons. For fraud, for our internal risk operations team, they need to understand why users are getting identity declined and what factors are enabling fraudulent users to slip through our fraud models. And we want to understand how each feature is impacting an individual user, not just a general feature importance. And we have millions of rows of data and hundreds of features. And someone might ask, like, why don't you just use an easily interpretable model like logistic regression? Well, simply we have found that logistic regression does not perform as well as random forest or XGB or other black box models. So we need a solution that allows us to interpret the effect of a feature on individual users and does so in a timely manner. So to do this, we implemented the Shapley values algorithm in Spark. So next slide. So what we're looking for, we want to find a solution where we can allocate surplus resources generated by the cooperations of players, or in our case, features. So we've all heard the saying, the whole is greater than the sum of its parts. How do we divide that surplus? So the way I like to think about this is like a trivia game. The number of unique questions a team gets right is higher when played together than if each player played alone and combined their answers. So by working together and collaborating, then players are able to get questions right that they would not have otherwise. And we want to be able to attribute not only how much did the individual bring to the table if they had worked alone, but how valuable are they as a collaborator. So let's go into the different properties we want for measuring contribution. Okay, so I'm going to go into each of these in more detail. So let's start with symmetry. Symmetry, equal contributions mean equal payouts. So this is pretty simple. If you're going out to eat with your friends, when two people eat the same thing, when splitting the bill, they should pay the same amount. And then next is dummy. So if you don't contribute anything, there's a value of 0. So if you go out to dinner with your friends and just have water, you won't have to pay anything. Our next one is additivity. So for this one, it's easier to think in machine learning terms. So let's think of a random forest model with 3 trees. You evaluate the marginal contribution of a feature for every tree, and you get 0.3, 0.2, and 0.25. When you average those contributions, you will get the same value as you would have if just evaluating the random forest model as a whole. So pretty cool. Next one is efficiency. So I think this one's pretty neat. So for an ML model, when you start with the average prediction, when you add or subtract the marginal contribution for each feature in the model, then you will get the final prediction for that sample's output. So you can use the Shapley values and the average prediction to get that sample's prediction. Okay, so we have our 4 properties. So what is the solution that includes these 4 properties? Shapley values, surprise. So Shapley value is a solution for game theory, and it's a way of defining payment proportional to each player's marginal contribution for all members of the group. It has all those properties we talked about. It was introduced in the 50s by Lloyd Shapley as a solution to a game theory problem, and it has since been used in machine learning for interpretability. So let's jump into an example so we can see how the math behind the algorithm works. Okay, we have a 4-feature model. We have the FICO score, the number of delinquencies, the loan amount, and also have they repaid specifically a firm before. And then let's go and look at the equation. Next slide, please. So here's the equation to determine the marginal contribution of feature J. We are going to walk through it over several slides. And first I want to talk about what we're summing over. So we are summing over all possible permutation orders for feature J. So why does permutation order matter? Next. We are trying to see not only how well this feature works, but also how well it works in combination with other features. In order to do this, we need to manufacture all possible scenarios of how a feature can interact with another feature or another feature set. So how can we do this? Permutations. So for our 4-feature model, then we're going to use in this example, our feature of interest is the loan amount. It can only be in 4 positions in that feature order: first, second, third, or fourth. For each of these, we only care about the permutations that have a different feature set prior to the loan amount. So everything before the loan amount in the permutation orders. And let's look at what all possible feature sets look like. So first, obviously if it's first, we don't care about anything else. If it's second, then it can only be combined with 3 possible features. And then if it's third, then it can only be combined with 3 possible feature sets. And then if it is last, then they all can only be combined in one way. So for each of these permutations, we need to compare how the model performs with and without our feature of interest. Let's pop back to our equation. Okay, so we now know all possible permutation orders for the loan amount, so we know what we're summing over. We know the place in the permutation order and the number of features. Now we need to be able to figure out the score with our feature of interest and the score prior to adding the feature of interest. So let's think about how we can do that. Next slide. So we need to compare the scores with and without our feature of interest and see how the results change. And next slide. So we're going to kind of put in the difference between those 2 scores into our equation. But how do we actually get the scores of the model with some features and not others in an efficient manner? We could retrain the model every time, but that is very slow and we'll miss some interaction. So what can we do instead? I'm seeing a black screen. Okay, I'm good now. Approximation. I like to think of this similarly to how you would create a partial dependence plot, where you hold some values constants and change others and see how the output changes. So we're going to talk about the Monte-Carlo approximation way of doing this that is used in ours and other Shapley packages that aren't on Spark, such as Shap. So Monte-Carlo approximation. Next slide, please. Okay. So we're going to start with an example. So we have our example customer, Taylor, who is applying for a $300 loan at a firm. Their FICO score is 600, and they have not repaid their loans with the firm before and have 1 delinquency on their credit report. And our black box model is going to take in all these features and output a probability estimate of their repayment. Okay? So what we need to do is get a sample a random permutation order And then we're also getting a random background user. So we have our random SAM, we have our permutation order. The next thing we do, next slide, please. We will use the permutation order and the random background user to estimate an approximation of the lone Shapley value. So we're doing this by creating two counterfactual instances. The first instance has all the features that are prior and including the loan amount from Taylor and everything else from the background user. And the other will have just the things prior to the loan amount. So have they been delinquent and what's their FICO score and from Taylor, and then the loan amount and have they repaid from the background user. So basically it will be able to calculate how much is that impacting it. Cool. So we're able to do this, and then we're able to get the marginal contribution for this permutation order and for this random background user for this loan amount. So can we go to the next slide? Okay, so we're able to create these outputs, and basically by the law of large numbers, with every permutation for many background users, we will eventually have a good approximation for the actual Shapley value. But as you might imagine, this is still not a quick process. So we decided to speed it up by implementing it in Spark, and let me hand it over to Isaac to talk about how we did that.
Thanks, Cristine. Yeah, so I'm going to talk about our implementation of this in Spark, which allows us to scale it for larger data sets and still have some reasonable throughput and latency. So yeah, basically we're just taking advantage of the fact that Spark will take a large data frame, which in this case will be our background data set, which is often the training data set, and will handle the logic of actually just splitting that up or partitioning that into several different instances. And also at the same time, Spark will take our model code and also put it, broadcast it, as it's called, onto every one of the instances. And so our logic just takes advantage of that. And concretely, going through an example here, we take our instance to investigate. So this is the same Taylor that we saw earlier. And so on every one of these instances, we have one partition of the training data set. So it's some subset of the number of rows. And the way that our logic works is basically it'll just go through all the rows here that that particular partition has, take the instance to investigate, do a bunch of stuff with permutations like Cristine was just saying, but basically just amounts to having these two counterfactual instances that differ by the feature value of the instance to investigate being here, 300 or not. And then simply run local to each executor, the black box model, to generate a prediction from each one of these counterfactual rows, giving us one sample of the marginal contribution. And so one of the things that this allows us to do actually is we can loop over all the rows and then try all of the different features at once with this presence absence logic in a kind of randomized way based on the permutation. And we'll ultimately get out these really tall Spark data frames that for each row will have name of the feature and the value from the, well, name of the feature and the value. So for example, this could say like having a loan amount of $300 and the marginal contribution, like one sample of the marginal contribution. Then another thing that this actually allows us to do fairly easily is that we don't see in other Shapley packages is implement weighted training data sets very easily by taking the weighted mean here. So we take the weighted mean of these marginal contributions, upweighting by rows from the training data set that correspond with higher weights from the training data set. And at the end of the day, we'll get out some Shapley values for each one of the feature values here. So the highlights of our implementation is that one of the big things is that it scales with data sets automatically using Spark. You can use data sets that are too big even to fit in a local machine. And also because of the way that it generates these counterfactuals, you get a huge batch of them. And so oftentimes it's faster to do batch prediction, i.e. predicting a lot of rows at once versus kind of like point inference predicting one. So we can get some runtime advantage out of that as well. And because of like the way that we iterate over the rows, we can reuse some of the rows for multiple different marginal contribution comparisons. And finally, as I mentioned, we can support training weights, which is important to a firm as a company because we're often predicting things like delinquency, which are very unbalanced, and we need to use training weights to, or I don't know if we need to, but it's helpful to use training weights to deal with that unbalanced data set. So here's some benchmarking that our colleague Shang did. And so basically he fit this toy model here using a kind of special uninterpretable, like using a special model form that doesn't have an existing kind of faster way of generating Spark values, or sorry, Shapley values. And he found that our method was a lot faster. I think this is normalized by CPU core. And in terms of the ranking was the same and had relatively small difference in actual Shapley value. Okay, so I want to now go through this quasi demo here to show how you would actually use this. And so for this demo, I'm going to be going through this notebook, and the notebook itself is available on our public GitHub, which there are links to in various places. But if you can't find that, it's also, you can just go to github.com/affirm/Shparkley. So yeah, so starting with this demo. So the first thing you need to do is, so I'm starting from a point of having a model that's already been fit on a training data set, and the training data set had 30,000 rows in it and 4 columns corresponding to the demo earlier. And so the next thing we want to do, if we want to actually explain a prediction from this model using the Shparkley package, is we import, well, first you have to install the package, which I've already done, obviously, and then you have to import these methods, and then you have to basically implement this interface. So what that consists of is subclassing this Shparkley model class and implementing these two methods, predict and get required features. Predict will take in a feature matrix, which is one per row of that you want to predict, and it'll give you back a list of floating point values. That's one per row again. It's fairly simple. And also get required features, which just says in order as a set the features that the model needs to predict. So I'm instantiating an instance of this subclass here and feeding it in this support vector classifier that I fit on the data. And the reason why I'm using support vector classifier is that it's one of the models that doesn't have like a faster way of computing Shapley values like some other models do. And so here I'm just testing the interface. It's getting the right features. All right, so then I'm going to load my training data set into Spark. By the way, this is something I did on my old laptop, which has like 8 cores. So that's why this has been automatically partitioned, this training data set into eight partitions. So that means we get like a parallelism of 8 here. So I'm asking it to explain the sample row here, which is the Taylor row that from Cristine's example earlier. And this row is actually just giving it, asking the model to predict, says, oh, okay, it's 99% likely to be delinquent. So you can ask, okay, why is that? So then the next thing we do is feed it through this compute Shapley for sample, which is from our package, feed it the Spark training data frame, feed it the model and the query row. And so now it's working. And there's 30,000 data points here that it's using to explain against. And so while that's running, we can look at our Spark job UI and see what actually is going on if we're bored or antsy or like want to make sure nothing's breaking. So you can do that, and you can see there's 8 tasks, 1 per each one of the executors here, and you can see, yeah, various stuff about what it's doing. Again, this was on my local laptop, so it's not as fast as it would be, on a cluster. Okay, so you can see that all 8 of the tasks finished, so the whole thing finished. And you can see it took about 50 seconds here, and we get back these Shapley values. And so we can check the efficiency property that Cristine described earlier. Basically means that the sum of the Shapley values plus the mean of the training data set should equal the actual prediction. And we see that that holds here because this assertion succeeds. And then we can actually visualize it. So to visualize it, I'm using the excellent Christopher Lundberg Shop packaged visualizer. This is the leading existing Python implementation of Shapley values. And it will helpfully show us that, okay, look, so the loan amount being $300 actually greatly increased our prediction here from almost nothing to nearly 100% likelihood of delinquent, and also the fact that this person had historically one delinquency had some impact as well. So I can now go through a little bit the using weighted training data set. So it's fairly simple, just feed it in the name of the Spark data frame that has the training weights. And I won't go through this computation, but you can see I did it earlier. And again, efficiency is still guaranteed. The interpretation is basically the same, although it looks like loan amount as compared to the weighted training data set is a little bit more important for this particular prediction being 99%. Okay, so now I'm going to show compared to the Shop package, which, as I mentioned, is the leading implementation. So the best explainer that the Shop package would have for this model form is the kernel explainer. So this is like an approximation again of the sort of brute force, which is going through all the permutations. So it's a little bit faster than the brute force, but it still takes a while, and you can see it spits out a warning that it might take a while, and it has some ideas about how to make it faster by downsampling or so on. But you can see that this eventually will finish and gives us basically the same results that we got with our Shparkley implementation in quite a bit less. We got it in quite a bit less time. Let's see, I think theirs takes about, skipping ahead here, all right, like 1 minute and 14 seconds. So yeah, so you can see ours is faster even on a local machine, and this is probably just because ours is using all 8 cores in my old laptop rather than this, which has to use 1 core. So that is the demo. So take home from the demo, we can use training weights. We can automatically scale using Spark. We get pretty good accuracy. And we also get some niceties from the Spark UI to see what's going on real time while it's computing and so on. Okay, so in conclusion, it's a lot faster than brute force, still faster than this kernel explainer, and we're very close to the Shapley values that you get from other implementations. And the open source implementation is available on GitHub, and we also put it into PyPy, so you can pip install it and try it out. I hope folks will do that. And now Cristine and I will be happy to answer any questions. Yeah, I guess folks can just type it into the chat and you can answer it probably.
free to post your questions in chat. The first one
Oh,
is...
it's just a video. Someone asked, how do I embed the IPy notebook? Yeah, it would be cool if I had a better way of doing it. Probably are better ways, but it's just a video.
Cool. And we also have some references, and we'll link the slides to be sent out with the rest of the presentation, the rest of the conference info. So if you want to learn more, there's a lot of good information there.
Thank you, Isaac and Cristine. So I'm going to clap for you. I wish there was a way for people to clap in the chat. Thank you so much. It was a great presentation. It is 12:01 Pacific time, 3:01 Eastern time. So we actually have an extended break now for lunch or snack or as you wish. So for the next 40 minutes. So we are going to take a break for the next 40 minutes and we'll see you soon.